Okay, Gen Chem kids, today we are going to talk about atomic theory. Now, our current atomic theory has taken us about 2,500 years to get to. We're going to do a very, very brief history of it today. So today I talk about a bunch of this is what I call my dead guys lecture, because we're talking about a bunch of dead white European guys today. So here we go. We're going to go back to ancient Greece for the first little bit. So, Chapter 2, Matter is made up of atoms. The current model of atoms is based on hundreds of years of work, if not thousands. We go back almost 2,500 years. Okay? So 440 BCE, we should probably put an E in there now, because that's not how we do things anymore. We just don't say BC, we say BCE. We had Empedocles. Now, he's probably not as famous as the other guy that also proposed this theory. Empedocles was the first guy who proposed this theory, but Aristotle is who really brought it out in the open, because guess what? Aristotle was a pretty popular and famous dude. So I'm going to put Aristotle here, because most people think of this as the Aristotelian theory of matter. Okay, so Empedocles, and later stolen by Aristotle, thought that matter was made up of just 4 elements. And those 4 elements are water, air, sometimes it's known as wind, earth, and fire. So a lot of you guys are familiar with this through the anime, The Last Airbender. We had water people, air people, or wind people, earth people, and fire people. So that's where they came up with that idea for that anime, is basically the Aristotelian or Empedoclean theory of matter. So this is the idea that they had here. So back in the day, when they really only had nature to observe, they didn't have microscopes or any fancy scientific equipment like we have now. This is where they came up with this idea. So Aristotle noticed trees and other plant life growing around in Greece. And, when you have trees growing, it's pretty easy to see that in order for a tree to live, you've got to have a couple of things. In order for a tree to live, you've got to have earth or dirt for that tree to be planted in. And if that tree does not get enough water, that tree dies. Okay? And then, when we took the tree and we chopped it down to make wood, I don't know if I can get a brown color here. Do I have more colors? I don't have brown. Okay, well, we'll just have to stick with blue. So if I chop this tree down and I make a little thing of wood, and I put that wood on a fire, I put logs on a fire and create a fire. Let's get some fire going here. We need some yellow here in the middle. If I burn that wood, I get fire out of here as well. So we've got earth, water, fire. And then when we are done with that wood at the very end, we have a bunch of ash. And ash is very much like earth. It looks like dirt again. So we've got this cycle. And if Aristotle and Empedocles were really observant, they'd know that trees also need air or wind to grow as well. And, if you've ever been near a really hot fire, you feel wind coming off of it just due to the heat differential and pressure convection cells that it sets up, but they didn't know about convection cells at that point. So I could see them maybe even thinking that the wind coming off of a really hot fire was just wind instead of pressure due to pressure differences. So this is what they were seeing. They were seeing these elements, earth, wind, water, and fire, just recycled over and over again in everything that they thought life was made up of. So that was the primary theory that was going on with matter. And that primary theory held sway for about 2,500 years, up until maybe 500 years ago. Not even 500 years ago. I want to say 300 years ago. Okay, that's how popular Aristotle was and Empedocles with their idea. About the same time, though, we've got this guy who's proposing a different theory. Okay, Democritus, better known for his theory, his political theory of democracy, which we in this country use for our form of government, modified a little bit from what Democritus proposed. Anyway, Democritus proposed that the world was made of two things. He proposed that it was made of atoms, and his idea of atoms was more of a thought experiment. He thought if you took something, say like an apple, let's make this red. If I take an apple, and this is a terrible apple, and I take that apple and I cut that apple in half. And then I cut that apple in half again and keep on cutting and cutting and cutting until eventually I get a piece so small of that apple that it's uncuttable. Okay? If I get a piece that is so small, it's uncuttable, but it's still apple, quote unquote apple. That's his idea of an atom. It's an uncuttable, small piece that still retains all the properties of whatever element or item that we're talking about. Okay? So atoms mean uncuttable. Okay? And the other thing that Democritus thought that made up matter was empty space. So he thought we had atoms and empty space. Okay? But, Democritus was not quite as popular of a guy as Aristotle. His ideas didn't get as much time in the academy at Athens. Go figure. And so his ideas were kind of lost for a long, long time. Okay? His ideas on government were also lost for a long, long time. It wasn't really until the Enlightenment that people started digging up Democritus's ideas on government, science, and all kinds of things. Okay, so here we go. Fast forward about 2,000 years. Okay, we have a French guy named Antoine Lavoisier. Now, Antoine was an interesting fellow. He was actually part of Napoleon Bonaparte's government. He was Napoleon Bonaparte's scientific minister. And Antoine Lavoisier was a very rich guy, and he got his wealth by marrying a very rich lady. Now, in those days, rich women were not, money usually didn't come with women. So he married well, which was usually the other way around. It was usually women were expected to marry well. And he used her money to do a whole bunch of experiments. Now, Antoine Lavoisier came up with this experiment. He, in fact, did several variations of this experiment. He took a candle. And when he took that candle and he burned that candle under a glass dome. And he burned that candle until that candle went out. And when he waited before he started the candle, And then he took the same glass dome with the candle that had burned a little bit. And now the candle is out, right? Because there's no more air in there. And he weighed this again. And he saw that the masses were the same. Even though we've melted or used up some of that candle. So where did that candle's mass go, even though we used some of that mass to burn that candle? Well, you and I know that when we burn that candle or we burn anything, it creates gases like carbon dioxide and maybe carbon monoxide and maybe even some methane or something when we burn something. And we get gases in the air. This glass jar collected those gases so they didn't go off. So he realized that the things that you start with in a reaction may be different than what you end up with, but the mass that you start with is always the same as the mass what you end up with. So this is his idea that he proposed, and it's a very important idea. He proposed that in ordinary chemical reactions, matter can be changed, like the candle changed, right? We don't have candle anymore after we burned it. But the matter cannot be created or destroyed. So this is known as the law of conservation of mass, meaning that the mass, let's change this color to red, the mass of our starting materials is always going to be equal to the mass of our ending materials. Okay, materials. We cannot create or destroy mass or matter. So whatever mass we start with is going to be the mass that we end up. We may change what we've made. We may have a chemical reaction or two going on and change the material and the combination of atoms, but the same types of atoms and the same number of atoms are going to still be there. They're just going to be rearranged. Okay, so that was a very important experiment that Antoine Lavoisier did from France. Okay, let's go on to our next guy. Okay, our next guy is Joseph Proust. He is from current Germany. Back then, Germany was not Germany. It was called Prussia. He observed that certain substances contain elements by the same ratio by mass. So consider table salt. He looked at table salt that was found in the Mediterranean Sea, the North Sea, the Atlantic Ocean, the Indian Ocean, the Red Sea. Regardless of where he found the salt, he found the same ratio of sodium to chlorine. And he found that that ratio never ever changes, regardless of where he got that salt from, or how big that sample, or how small that sample of sodium chloride or table salt was. So Joseph Proust calls this the law of constant proportions. Constant proportions. Okay, now this means that I can't write. Okay, so that means that regardless of where we found table salt, we are always going to find NaCl. We're always going to have one sodium for every one chloride. So 1 to 1, we will always have this ratio, regardless of where we get our table salt from in the world. even the table salt that we dig up here in Utah in the salt mines down near near Moab, and the salt factory that we have out, if you've ever driven out past Tooele at the Morton Salt, it's all NaCl. It's all 1-to-1 ratio, regardless of where in the world we get it. Okay, so this is what this states. It says a chemical compound compound always contains the same, I should make that an M. That's really not an M. The same elements combined together in the same proportion. By mass. So if I am looking at water, I will always have hydrogen and oxygen. I will always have 2 hydrogen atoms for every 1 oxygen atom. Although at this point, they really didn't know atoms. They always knew that I would have a mass of 2 hydrogens to every mass of 16 oxygen at that point. So they knew that regardless of where I found water in the world, it would always have that ratio. Wherever we found salt in the world, it would always have a ratio of 23 sodiums to a mass of 35 chlorines. They would always find that everywhere, okay? And then comes along Dalton. Now, Dalton is a British guy. He's actually a Quaker, and he's a studious guy. He likes to read a lot, and this is where he gets most of his information, is basically by reading and putting together ideas that different scientists missed when they were putting together their own papers. He did a bit of experimenting by himself, but he really was great, like awesome at synthesizing other people's information into even bigger ideas than they could do themselves. He actually came up with about 6 ideas. So let's write them down. And I'm going to try and make each idea a different color so that they don't blend into each other. Okay? So his first big idea is that all matter consists of indivisible particles called atoms. Okay, so Dalton thought of an atom as a big round ball. He thought of it as a billiard ball. Now, those of us in the United States really don't know what billiards are. In England, across the Atlantic Ocean, they call pool billiards. So he thought of atoms as pool balls, big, hard balls that are unbreakable, indestructible. That's what he thought of as atoms. Okay, let's do another color so that we can do this next one. Okay, idea number 2. Atoms of the same element are the same size. Shape and mass. And they are different from other atoms of different elements. So if I look at an atom that has the same mass as another atom, they have to be the same type of atom. If I have a different mass, it's going to be a different element. Okay, so I can tell by size and shape and mass what element I have. Okay, our next idea here is atoms cannot be created or destroyed. So I'm going to make this 3. Atoms cannot be created or destroyed. Oh, I just totally misspelled that. Okay, let's fix that. Okay, idea number 4. Actually, let's do this. Idea number 4. Atoms of different elements may combine with each other in fixed simple whole number ratios. So for example, carbon dioxide, I have 1 carbon and I have 2 oxygen. I will always have that same ratio in that same number for every carbon dioxide. So that's the idea of Dalton, fixed simple whole number ratios for whenever we make a compound. Okay, next idea number 5. Well, I want that to be green. Okay. Atoms of different elements can combine in more than one ratio. So atoms can combine in more than one ratio to form different compounds or to make different compounds. Come on, erase. Okay, so I can do more than one ratio to make different things. Here's an example. I can have H2O, 2 hydrogens and 1 oxygen to make water. Or I could go H2O2. That is better known as hydrogen peroxide. I have 2 hydrogens, 2 oxygens. I don't think hydrogen peroxide and water are nearly the same. They're both made out of hydrogen and oxygen, but they react and behave totally differently. Same elements, different ratios make different things. Okay? And the last of Dalton's ideas, idea number 6. Atoms are the smallest unit of matter. Okay? Atoms are the smallest unit of matter. that can take part in a chemical reaction. Okay, so if we're going to have a chemical reaction, we have to work with whole atoms. Okay, so these are the 6 main ideas of Dalton. And notice this was, less than 200 years ago by the time he passed away. So we're getting pretty, in terms of history, we're getting pretty modern. Okay, next guy, another English guy. This guy is Joseph John Thomson, otherwise known as J.J. Thomson. Notice it's 1897, so we're just like 125 years ago. In terms of history, not very long ago. Back in the 1890s, the thing that was experimenters were playing with, that was all the rage, was electricity. If you know anything about American history, especially in the New York Niagara Valley of the 1890s, this is when Edison and Tesla were having their electric wars. I mean, everything was about electricity. We wanted to harness electricity. We wanted to be able to use it. We wanted to be able to use it for manufacturing and power and create all the electricity and all the things that we take for granted now. Okay. Well, even in England, people were experimenting with electricity. So J.J. Thomson, he was playing around with a cathode ray tube, and I will also put a video of this experiment in here so that you can see kind of what he was doing. I don't have a cathode ray tube at Murray High, so we're going to have to use my colleague's video because he actually does have a cathode ray tube. And he was able to realize that there are smaller things than an atom. Now remember, up here on idea number 1 for Mr. Dalton, all matter consists of indivisible. Dalton thought that atoms were indivisible. So we thought the smallest thing ever was a hydrogen atom. J.J. Thomson was playing with a cathode ray tube, and he played around with a magnet, and he realized that the cathode ray in that tube was deflectable by a magnet, and it was attracted to the positive side of the magnet. And he originally called this particle that he was able to find a corpuscle, but we don't call them corpuscles. We call them electrons. And he realized with a very interesting experiment that he did, it was actually Millikan that did this experiment. Millikan isolated electrons, and he realized that electrons were 1,847th the mass of a hydrogen atom. So very, very small, much smaller than a hydrogen atom. Now remember, we thought up until this point that hydrogen was the smallest thing that we had. They just found a charged particle that was charged negatively and smaller than hydrogen. So this is our first subatomic element, or not element, but particle. And we call it an electron. We symbolize an electron with an E, with a negative sign up on the upper right-hand side. So E negative is electrode. This is what a cathode ray tube looks like. I will embed the video of that demo. Okay, so J.J. Thomson realized that, when we go around touching everything, it doesn't shock us. And if it was always negative like that electron, we would have electric current running through us when we touch everything. And that's not what happens. We know that things have to be neutrally charged. So Thomson thought about it. He realized that if I have a negatively charged thing in that atom, I also have to have a positively charged thing in that atom to balance that charge. So he went about trying to figure out what that positively charged thing was. He found that second subatomic particle, and he found that it had the same amount of electric charge as an electron. However, the charge was opposite. So instead of being negative like the electron, it was positive. These particles are called protons. And we symbolize protons with a lowercase p and a plus in the upper right-hand corner. Okay, Thomson calculated the mass to be about 1,836 times that of an electron, or about the same size as a hydrogen atom. So we know that the vast majority of the mass coming from the atom is coming from the proton, not the electron. Okay, so this is the way Thomson thought of an atom. He thought the atom was this positively charged matrix that just had positive charge all through that pink matrix. And then randomly studded in this positively charged matrix were the electrons, just randomly in there. Now, being the British guy that he was, he thought it would be a lot like this classic British Christmas dessert. It's called plum pudding. Notice we have little bits of the chopped up plums randomly distributed in that plum pudding. Now in Britain, pudding is actually cake. Okay, so this is plum cake for those of us here in America, in the United States. So this is what is known as the plum pudding model. Now, for those of us here that really don't eat plum pudding, I think of this for us American people as chocolate chip cookies. So he thought of the positive matrix kind of like the cookie dough that was just made basically the cookie. And he thought of the electrons as the chocolate chips, the randomly distributed bits and pieces of chocolate throughout that cookie were the electrons. So that gives you kind of a more idea of the atomic theory that we have. We are going to stop at this. Our next guy is Rutherford. He was actually not from Europe, even though he looks European. He was European descent, but he was a Kiwi. He was from New Zealand, a lot like our principal, Mr. Wahangi. He's also from New Zealand as well, so he's a fellow Kiwi. But we're going to cut it here. We're going to do a PhET laboratory with what Rutherford did and hopefully have you experiment a little bit before we talk about it. We'll see you later. Bye.